So now we're going to work through an example here to find the best fit line using linear regression while using Desmos to find it. So in this example, we have the speed for selected stride lengths, the distance it covered when you take 2 steps, given to us here in this table. And the top row, we have their stride length, and then the bottom row, we have their corresponding speed that they were going. And with this, their speed is dependent on what their stride length is. So that means speed is our y, and then the stride length is the x variables in this. So we have 8 ordered pairs essentially, 2.5, 3.4, 3.0, 4.9, and so on, that we need to essentially plot on a graph and get the best fit line that goes through them. We're going to do this by going to Desmos.com and clicking on the plus sign in the upper left corner and selecting a table so that we can enter this data that we have into the table. After that, we're going to go to the next line on the calculator and input this equation. Y1 is approximately mx1 plus b. And when we do that, it's going to tell us what m and b should be for the best fit line. So now let's switch over to Desmos.com. When you go to Desmos.com, it's going to look like this, and you're going to want to click the graphing calculator button. And now you can see that we have a plus sign in the top left corner. If we click that, then we're going to have the table. And now this is where you would want to go to your data set and input all of the values. So 2.5 for x, and that has a corresponding 3.4 for y. And then we can see it plotted that point over here on the right as that green dot. I'm going to skip through plotting all of these points because it's going to take a while, and switch over to all of them already on the graph here. So the table is filled in, and we can see all 8 of the data points are on the graph. Zoomed out a little bit to be able to see all of them. And now I want to enter that equation that I showed on the worksheet. So I'm going to have y underscore 1, and then we need to approximate that with our tilde symbol. And then we're going to have m times x underscore 1, and then we have plus, and then b. And now if I zoom in over here on the left, we can see that we have some parameters that it says. It gives us that m is equal to 2.73026, and b is equal to negative 3.31645. And now that's what we can use for our slope and our y-intercept. So now we can write our equation. On here, I want to round m and b to 3 decimal places. So this means my m is going to be 2.730, and b, we're going to round that to negative 3.316. So our equation now of the best fit line is y equal to 2.730x minus 3.316. The next one, we're asked what is the slope of the line, and what does this tell us about the stride lengths of an adult? Well, we already have the slope, that's the 2.730. And now what does this mean? Well, our slope, we find that by looking at change in y over change in x. So our y is the speed, and that's being divided by the stride length then. So they have a speed of 2.73. Their speed increases by 2.73 meters per second, every time their stride length increases by 1 meter. So a 1 meter increase of their stride length means that their speed is increasing by 2.73 meters per second. The next, we're asked what is the vertical intercept and what do we get from that? Well, our y-intercept is b, which we have as being negative 3.316. And maybe let's write this as the ordered pair because that also will help understand what this would be. And our ordered pair for the y-intercept means that x is 0. So this is 0, comma, negative 3.316. And now we said that x was the stride length, while the y is their speed. So now this y-intercept, if I were to write a sentence to say what this means, we could say if their stride length is 0, then their speed is negative 3.316 meters per second, which obviously doesn't make a whole lot of sense. And that is because we're looking outside of our reasonable data points, which we'll get to in a little bit here. But I have one last problem here that I want to do before we go on to our reasonable data points for this. And this is to predict the average speed of an adult man for a stride length of 3.4 meters. So 3.4 meters, that means I want to replace x in my equation with 3.4. So we have y equal to 2.730 times 3.4 minus 3.316. And now this we can then evaluate in our calculator. And you should then get 5.966. And this is our y, which has a unit of meters per second. So now I want to go back to our reasonable data points for this data set, and this is what we are essentially calling domain and range. Domain is all of our possible x values that we could have for our data, and our range is all of our possible y values that we could get back from this. And to be able to find this, I want to sort of look at both my table and our graph. So on my table, if we notice, my lowest x value is 2.5, and my highest x value is 4.5. That means my domain is essentially between those values. I can round them a little bit to extend a little bit and say my domain is between 2 and 5. And we write it in this notation called interval notation, which is given with these brackets to say that I am between the values of 2 and 5. And then my range, I'm going to do the same thing, but look at the y values for this to see what my y values would have been. So here, if we look at the table, my lowest y value is 3.4, and the highest y value is 8.7. So maybe we can round those a little bit and say that our range is going from like 2 to 10 for a reasonable range that we might have for this model. And now a little bit about why that y-intercept doesn't make sense. It's because it's not the x value that we put in of 0 for that y-intercept is not in our domain. When we look at things within the domain, that's called interpolation. And that should be relatively good prediction for what that data should represent when we're looking at data points inside of our domain. However, if we go outside of that domain and look outside of our range of data points that we have, that's called extrapolation, and it's less reliable. It's not going to be as accurate, and a lot of times the information that we would get from that might not make sense. Just like how the y-intercept for this, our statement for that, didn't make any sense.